Hello everyone, I am Quoc-Cuong. Today I will talk about our work in JV challenge on video object segmentation interactive scenario. The speech will consist of four main parts: interactive video object segmentation introduction, proposed method, experimental results, and our conclusion. The interactive scenario assumes that the user gives iterative refinement inputs to the algorithm, in this case in the form of scribble, to segment the object of interest. In the first interaction of each sequence of frames, the server chooses a certain frame and provides a human annotated scribble for each object in this frame. The user submits segmentation masks of those objects for all the frames to the server in each of the subsequent interactions from a list of frames specified by the user. The server chooses the frame with the word prediction and provides a new set of human simulated scribble in this frame. This procedure is repeated until a maximum number of interactions or timeout is reached. Our method maintains for each sequence a memory pool that is global across interactions. This pool only holds frames and corresponding masks that are deemed reliable. For each sequence in each interaction, the scribble to mask module will use the user scribbles along with the possibility available mask inferred from the previous interaction to generate an initial mask. This initial mask is further refined by the self-reference refinement module to generate a refined mask. This refined mask will be deemed reliable and is added to the global memory pool. The guided mask propagation module will use this refined mask as an initiator to generate segmentation masks for the entire video with reference to the aforementioned global memory pool. In the following sessions, we will deconstruct each of the components of our method. The input scribbles are first converted into control points using a control point extractor. These control points will be used by a control points to mask module to generate a complete multi-object segmentation mask. If it is not the first interaction, a previously inferred mask is available and will be combined with this mask to generate the initial mask necessary for the next steps. Each scribble part can be converted into a set of evenly sampled points along the path. Each of these control points holds the information about its coordinates on the image and the object to which it belongs. To generate an individual object map from the image, the propagating refinement algorithm takes as input two sets of points. We consider control points belonging to that object positive point and control points belonging to other objects, often including the background class, as negative points. The control points to mask module will generate a probability mask for each object, all of which can be merged to generate the object mask. Here, we show an example of the whole procedure of scribbles to mask. You can see in the first arrow, the green scribble corresponding to the human instance and the red scribble corresponding to the recycled instance are converted into control points, visualized as small dots. Then, each instance gets its own predicted mask. The brightness of each pixel indicates the level of confidence of the model. Individual masks are merged into one segmentation mask with the same color code. For the next part, we digress to first talk about the core algorithm used in the remaining components, memory-based video object segmentation module. These modules maintain a memory pool that can be filled with frames and their corresponding masks. They will perform segmentation on a frame with reference to that memory pool. We use this model in two different ways: as a refinement mechanism in the self-reference refinement module and as a mask propagator in the guided mask propagation module. In our work, we utilize the space-time memory network module, abbreviated as STM from here, as a memory-based module. It has two operations: to memorize a frame mask pair and to segment with reference to the memory. Naturally, our method relies heavily on the quality of the memory fragments stored in the global memory pool. The most important fragments are the strippable frames obtained after each interaction. Another set of frames to consider are the reliable infer frames, the predicted masks that are considered reliable obtained throughout the propagation process. These frames go through a filter to delete non-informative frames such as blurries, deformation frames, which will eventually be enriched to improve memory pool quality. As a refinement mechanism, the memory-based module maintains a local memory pool that memorizes all the previously inferred masks and uses that memory pool to perform segmentation on the same frame again, hence the name self-reference. It is also possible to initialize the local pool with a aforementioned global pool. Here, some examples of how this mechanism have refined the initial mask. The example on the left shows how it can help with under segmentation case, specifically better boundary snapping and hole filling. The second example shows how it can also help with over segmentation case, specifically with long thin objects, albeit not perfectly. Init interaction with the refined frame as an initiator. The propagation goes in two different to both ends of the video sequence. However, the process does not go all the way, but instead at a length calculated by considering the indices of the annotated frames in previous interactions. As can be seen from the diagram, it starts midway between the current annotated frame index and the nearest previous annotated frame index. Considering the possible decay from the accumulated error of any propagation algorithm, this is a reasonable approach as all frames are only influenced by exclusively reliable frame. To counter the problem of misidentification or over-segmentation, we employ a guidance mechanism in our propagation module. It uses a predicted mask of neighboring frames to generate a localization mask. This mask is used to mask up potentially unrelated surroundings so that the segmentation algorithm can have a better focus on what to segment. Here are some qualitative results. Here we show the graph of the J and F score after each interaction. For each sequence, more interaction means a larger global memory pool and consequently, more reference for the memory-based segmentation module. It is as expected that the J and F score see a progressive increase after each interaction. Our proposed method achieves 0.767 and 0.759 in terms of area under the curve and J and F at 60 seconds, respectively, ranking second in the interactive scenario of the 2020 David Challenge. In conclusion, we present a fast and efficient method for interactive video object segmentation that utilizes three key modules: control point-based strippable to mask, self-reference refinement, and guided smart propagation. The strong performance of our method is proven by good performance, both qualitatively and quantitatively, from the result of this year's challenge. We conclude this week with some direction for further research. 1. The strippable return from the server from the second interaction onward can be better leveraged to refine previous predictions. 2. We need a better system to evaluate and decide which frame to be added into the memory pool. 3. Mass propagation should be guided by a better flow-based tracking method. That's all. Thank you for your attention.